Yeah, and that's why I was going I don't know how that
It's weird.
Not the video.
I don't think so.
There is a little noise in that video, but I don't think. Oh, it's not really a video. It's actually a series of stills.
We just close up everything that's open and might be making noise. Yeah, if it gets noisy, we can just disconnect the speaker for now. It'll only be John that needs that. This isn't. Here we go. I think we're ready. We are. We're on YouTube. Are we on YouTube? Be on. All right, I think we're good.
Hello. Hi, everybody. I'm Jan Rush. I'm president of DVAA, and I welcome you all here tonight, and welcome to everybody joining us on YouTube. I want to thank Tom Nolasco, our VP, for leading the meeting last month. I was off in Hawaii visiting my new grandson, and while I was there, this happened. Kilauea erupted. And it was, maybe hit the lights so everybody can get more impressed. It is so amazing to believe that we are living on this hot ball of raging fire. There were two fountains, and one of them was 300 feet high. We were at about a mile and a half away. Nice safe distances where they keep you, but it was really impressive. And I have a little video here that hopefully will play to give you a little bit more of a feel of how it looks. Sorry about the noise. Those are the people in the background being amazed. And it was really cool. When it starts to erupt, the eruptions can be very short as 13 hours. So basically, if you've ever been to the Big Island, you know that most of the tourist areas are pretty far from the volcano's park. So you get in your car and you drive off and you try to find a place to stay while you're on the road, you know, it's that kind of a thing. So, but it was really fun.
How far away were these pictures taken?
A mile and a half.
Could you feel the heat?
No, couldn't feel the heat. You could hear it. The noise was extremely impressive. Yeah. So that was a fun little adventure. Probably not as adventurous as seeing my grandson, but close. Okay, well, closer to home, we had a little bit of a disappointing night around here. Did anybody see the eclipse? Was anybody far enough away? Yes, all right, great. Part of it, right. So,
For 5 seconds.
yeah, so here's the cloud bank here, here's me, and I just thought it was interesting. Here's a video from Stan Williams, and it shows you exactly how it was nice until it got to totality and then nothing. Pretty much what I saw. And then nothing. Oh, well. That's the way our hobby is, I'm afraid. But if you were hanging out with Dan Stern in Florida, this is what you got to see. And he got this nice composite here with all the phases. Really nice. Thanks, Dan, for sharing that. Okay, on to our upcoming events. Well, this has been a horrific week for me. Sorry. Trying to pin down where things stood on our Air and Space Museum bus trip, because the Smithsonian closes if there's a government shutdown. And as you know, we've been worried about that. So the latest thing is that the Senate has voted that we're not going to have a shutdown, so we are going tomorrow. So everybody who's signed up, don't forget to show up. We're meeting not here in the Radnor parking lot because they didn't have room for all our cars in the bus. We're meeting at a separate spot, which is, there's a map on the website for those of you joining us. And there are, because of cancellations, 3 spots left. So if anyone wants to go, you can actually jump on to the website tonight or I don't know, yeah, tonight sometime. And first come, first serve. There are 3 spots on the bus.
Does this mean the Senate is actually more reliable than the weather?
I think that's what it means.
Oh, Senate.
Okay, and on March 22nd, we have indoor winter clinics, and I'm going to say a little bit more about those in a minute. As you know, we have a partial solar eclipse on March 29th. It's going to be very tough, though. It's only for like a minute, 2 or 3 minutes right after sunrise. So you need a really low horizon to see it, but Barry found a spot, right, Barry?
Yes.
You want to mention it?
I found a place on Pot Shop Road in Montgomery County where you can see it. It's about 10 minutes.
So if you want to get up early and go see a partial solar eclipse.
The Abington High School is a fairly high spot with good visibility, pretty much 360 degrees.
Okay, Abington High School. All right, we got 2 suggestions for that. April 2nd, we have an Anderson Farm Park Star Party. Stan Williams is leading that. April 5th, we have the Public Star Party at Valley Forge. And we had a great star party last month, I hear. Joe Kraus was captain for that. We had a super turnout and lots of telescopes. So it was lots of fun. So I think as the weather warms up, it'll get even more fun. And of course, we have an astrophotography workshop on April 9th and a monthly meeting again here on April 11th. And that is the joint meeting with the physics teachers, right? Okay. So that's always fun. We have a new group or visitors that are fun to talk with. Smart people fun to talk with. Okay, so in the middle of last year, we polled people about what they'd like in the way of topics for clinics that we could offer. And we're working our way through that list, and the last 2 we're offering in March, on March 22nd. But right now, we don't have enough signups to hold the clinics. So if you're interested at all, do sign up because they might not happen unless we get 8 people. And I'm going to tell you a little bit about the 2 clinics. The first one, they're both March 22nd in this room. The first is a beginner observer telescope and sky guide led by Tom Nolasco. And it's things like, is my telescope okay? Is it working right? I'd like to tell you what's happening with my telescope. Can you tell me if something's wrong? What's field of view? Do I really need to bother aligning up my finder scope? How magnified is the object that I'm looking at? And why does everybody talk about seeing? And lots of tips to make your telescope viewing more enjoyable. So yes, it is for beginners. But if you're an intermediate and you have questions about some of those things, it's really good to have a one-on-one conversation with your fellow observers and with the people leading the workshop. It's always a good thing. So if you'd like to do that, sign up on the website, because otherwise it might not happen. Okay, second one is going to be led by Jeremy, and this is about dark sky observing and overnight star parties. So things like, how do I find the best and darkest place to observe that's close to my home? Do I need to drive so far? Why are we talking about this? What are the rules of dark sky observing? And with today's gadgetry, that is smart telescopes, do dark skies have any advantages? Maybe you don't need them. So if you have questions about any of those things, come to the workshop. Okay, we also have an overnight star party, which we've been talking about for a couple of months now. This is the star party at the Big and Little Dipper Lodges, April 23rd to 26th. Now, you don't need to stay that whole time. The reason we booked those 4 days is to increase the chances that we'll have clear skies on at least 1, 2, maybe 3 of those. So it's a combination of private bedrooms, rooms that are beds that are in more of a dorm-like setting with multiple beds in the same room, and then camping. So right now the situation is that the private bedrooms are full, but we do have 4 spaces with beds. And these are regular beds. They're not like bunk beds or anything. Regular beds is just that you're in a room with 4 or 5 people. And we have unlimited camping spots. So if you're interested in that, please sign up before the bedrooms disappear, or before the beds disappear.
Yeah, electrical connection, what does that mean?
Electrical connection?
In the field?
Yeah.
No, there's one post that, let me rephrase, there's 2 areas you can get electric in the field, but I wouldn't rely on it. If you look where that black, well, actually, maybe it's Gary's van right there. I think that's where there's one post that has maybe 4 outlets, if I recall, Tom.
Here somewhere?
The pavilion has 2 outlets over there. The pavilion's off to the right.
Because the sign up online said that you wanted to electricity.
Uh-huh.
Yeah, so the reason I put that in there is just so, we're aware of kind of what the demand will be. If you absolutely need electric, like, for instance, I would take batteries and solar panels and stuff and just recharge everything right there and rely on the battery power, because I don't really need electric. It's nice to have. But if you need electric, you don't have any other options, then you would have first dibs on that.
Okay. All righty, now we have our reports. Welcoming report from Brian Lee.
I'm Brian Lee, I'm welcoming chair. We have 9 new members this month. Carson Spaniel, Sean Black, I know he's here tonight. Nick Bunio, Peter Pickens, Eric Kirchberg, Robert Smith, Timothy Morrow, Michael and Denise Aguilar. So let's make them feel welcome.
Could you stand if Brian read your name? Okay. Great.
And a shout out to Lou Viveris if he's watching.
Yes. Guess you could turn the lights on, Brian, so we can see these people. I'm gonna make them stand up again.
Swearing them.
Can we have our new members stand up again so we can all see your faces? Great. Anybody here for the first time tonight? Ah, welcome. Welcome to all of you. And come up and see me afterwards and introduce yourself and say hello. Yes, the shout out to Lou Varvarizes is that one of our members, Lou Varvarizes, is having surgery on Wednesday, and there's a get well card back on the table there. So we'd like anyone who knows Lou to sign it, and you can give him your best wishes. It's got a big operation on Wednesday. I guess now we're ready for our observing report, which is going to be given by Alan Purdy, talking about treasures in the Great Bear. Do you like that? Okay.
Okay, with springtime coming up, I want to introduce you to a number of things that you can see in Ursa Major.
Other button. It's always the opposite of what you think.
Oh, okay. Now, somebody way back when had a good imagination, and they looked up and they saw this, to them looked like a bear, but I don't know too many bears with long tails. But that's what we're dealing with. But within that constellation of Ursa Major, we do have a whole treasure trove of objects that will appeal to almost everybody. So let's take a look at a sampling of the treasure chest. This is an image of from my atlas that I use. It's upside down on purpose, but I have to mention that whenever I open my atlas at home to look something up or to do some homework prior to an observing session, if my wife is around, she gets this crazy wild look in her face and grabs a pencil and wants to play connect the dots. And that's essentially what we do when we're out in the sky. And when it's clear, we're mentally connecting the dots. And we all know the asterism, the Big Dipper, which is the body and the tail of the bear. But those are composed of mostly 2 or 3 magnitude 2 and 3 stars. So they're fairly bright. We can see them from Valley Forge. If you go to a little bit of darker place, we can see the other stars that are maybe 3 or 4th magnitude that make up the rest of the bear. So if we continue, we can see the head, the forelimbs, and then the hind limbs. And the entire constellation is quite large. And there's a lot of different objects within that constellation for you to enjoy. And one of the things that is very easy to show at star parties are some double stars, and you know what I'm going to be talking about next, and that is Alcor and Mizar. And you don't need a good eyesight. You do need good eyesight to see the fainter member of that double star. And usually I ask younger folks, younger than me, and they can actually see that. But a little bit of magnification will show wrong one. Will show the dimmer star, Alcor, and the brighter star that looks like a single star naked eye is actually a nice double. But one of the reasons that the Alcor is a little dimmer is 10 light years further away than the other 2. So it's just a line of sight double star. And you don't need too much magnification to split the true double. Now, somewhere in between the two pointer stars right here is a very pretty double star, a blue and a yellow star is the Struve 1495, but it appeals if you like the aesthetics of color. And it has a position angle of 38 degrees, which means if north is 0 degrees and 90 is east in your eyepiece, then you draw a line between the primary and the secondary and intersects a point roughly about 38 degrees. So that's their double stars are known for their position angles. Drawing a line between eta and zeta, and then make an equilateral triangle with those two stars, we come to a Messier object that's M101. And M101 is a nice face-on spiral galaxy, 28 million light years away, and about a quarter degree across, so it's fairly large. And just off the tip of the bottom of the Dipper, I should mention that the British people call this the plow. We call it the Big Dipper. It looks like a farmer's plow. But right off the edge of that is another Messier object, and that's in 109. And that's a barred spiral. You can see the bar right here in the core and the spiral arms. The Hubble Space Telescope is showing a lot of collections of dust clouds blocking the background starlight. Going back to the two pointer stars, we can find our way to Polaris, and that's an easy way to find approximately where north is. Now, drawing another line between gamma and alpha, and going the same distance beyond that, is a nice duo, Messier objects, M81 and M82. And that's frequently imaged by a number of people. They're both, one is a nice spiral galaxy, M81. M82 is an irregular galaxy, but both are about the same distance from us. And with a wide field view, both can be seen within about a degree or so. So you can get a 2-for-1 in a very nice low power eyepiece field. This is an image from another atlas that I use. It's the Pocket Sky Atlas, the jumbo size, because it's easy to read. And I use it to look at variable stars. And you see the colored arrows, which is a hint that I got from John Badelschmidt a number of years ago. So thanks, John, for the hint. Putting these colored arrows on an atlas, if you use paper atlases, makes it a lot easier for you to find something in the dark instead of hunting around with a red light, trying to find where is that particular object. You've got these on your atlas, and you can see them a lot easier and quicker. It makes for more efficient observing session. So Ursa Major has a number of variable stars, and these are stars that vary in their magnitude. And what I want to do is give you one example, and that's RY Ursa Majoris right up here. And for reference, also there's a smaller, fainter star called 74 Ursa Majoris. I just want to point those two out because on the next chart, we're going to see those two. This is a chart that one can print out either from the website of the Association of American Variable Star Observers, AAVSO. You can print them out for binoculars, you can print them out for telescopes, but it gives you the variable star and number of stars with known magnitudes that do not vary. And so nearby there's a star that has 67, that's 6.7 magnitude. Over here there's 7.4. They leave the decimal points out on purpose because the decimal points look like stars and can get a little confusing. So what I've done and what you can do with a pair of binoculars, you find the area in binoculars. You find that variable star and you ask yourself, is it brighter or dimmer than that 6.7? Is it brighter or dimmer than 7.8? And you kind of get a sense for about what magnitude it is on that particular night. And so using that, and there's that reference star down there. I wrote in the name of that star. And over the last 5 years, these are the magnitudes that I've come up with binoculars for that particular star. And so back in last July was 6.7, which means that's a variable star looked very identical to that 6.7 non-variable star. Last Saturday I went out with binoculars and recorded that as a 7.3. So it was definitely dimmer than 6.7, a little bit brighter than that 7.4. So I wrote down 7.3. But what does that mean? What does all this mean? What can you do with that information? You can upload your observations and your guesstimates, either visual or notice a lot of people on the chat or want to do it electronically, you can do that as well. So the ASO takes all of these hundreds of observations by other people, and they make a graph over a period of time. So this is the variation of that one particular variable star in Ursa Major. And going from peak to peak is about 310 days, which is kind of a long period. There are other variable stars that are much faster and don't have such a long period. But any change in that period can be noticed by people like yourself who are monitoring this whenever possible and uploading the information. And if there's a change in the period, then that tells the other folks that something's going on and requires more analysis. So you're doing a little bit of citizen science by doing that. Ursa Major is also home to a number of asterisms. The Big Dipper is one asterism. There's something called the Broken Engagement Ring, which is about down over here. And there's a bright star with a faint ring of stars nearby, and somebody with imagination called it a broken engagement ring. But if you go to Polaris, Polaris is also part of an asterism called the engagement ring. Polaris itself, a magnitude 2 star, is a diamond, and there's a faint ring of stars that you probably really didn't notice it, but the next time you are pointing your telescope at the Polaris, take a look at that faint ring of stars, and that is called the engagement ring. There are others here called, the handle of the Dipper, plus a couple other stars, looks like a gas pump handle. The part of the front legs looks like a spade. So there's some other names as well. So a little imagination is required. What else do we have? A number of Herschel objects. These are like Messier objects, but a little smaller, a little dimmer. And this is an image that John Leingruber took last year. Thanks, John, if you're on Zoom. On YouTube for letting me use this. He took this image of NGC 3079, which is about 50 million light years away. But also in the same image, he got a twin quasar. That is a quasar that's gravitationally lensed by a foreground galaxy. So this is 8.8 billion light years away. So in one image, you got something that's 50 million light years away and 8.8 billion light years away. So another 2-for-1 capture by this image. And the Cookie Monster likes quasars. I looked at, there are at least, there are more than 24 quasars in Ursa Major that are brighter than 16th magnitude. And there are probably many more that are much dimmer than that. So, so don't tell him, you grab him first. Now, what do we have in the treasure chest of the Great Bear? Well, we've mentioned Leslie objects. There are 7 of those. There are 178 Herschel objects. There are a number of double stars, a number of variable stars. As I mentioned, there are over 24, a number of astronauts, I should say. And also there are over 24 quasars. So the next opportunity you have, take both hands, grab into the treasure chest, see what you come up with, and then repeat as necessary. And enjoy. There's lots out there. All right, thank you.
Thank you. Covered a lot of ground in a very enjoyable way.
Okay, on to Jeremy Carlo, our programs chair, who's going to introduce our featured speaker.
All right, thanks, Jen. Let's see, let's get some more interesting up here. John should be coming back pretty soon.
I am back.
All right. You'll get
Can you hear me?
in just a minute. Yeah, we can hear you.
Okay.
All right, usually I write something down, but this is one of those crazy days, so I'm just gonna have to go by memory. A little bit about upcoming programs. So in April, as Jan said, we're gonna have a joint meeting with the American Association of Physics Teachers. And our invited speaker will be Professor Christy Love from Drexel University. She's gonna be telling us about citizen science using neutrino astronomy. In May, we're gonna have Professor Dave Chus from Villanova University, also my boss. Everybody has to be on their best behavior. He'll be talking about the magnetic field in the center of the Milky Way galaxy. June is open right now, so we're working on that. In July, we'll have one of our returning champions, Bart Freed. He'll be coming down from New York, probably to tell us about some old telescopes and some new work on them. And in August, we're going to have Don McCallerman, another of our returning champions, and he's going to tell us about his exploits in radio astronomy. Do you want to give a little preview?
Well, it's low frequency, it's 20 megahertz. So when I say radio astronomy, I'm not in gigahertz. This is 20 megahertz, big antennas, but just for the sun and Jupiter only, nothing else. So stay tuned.
Something you can actually do when it's cloudy, so yeah, and during the day too.
Yeah.
Well, for the sun, it has to be during the day. All right, so that's the next couple of months. Oh, in September, we're going to have an outdoor meeting at Fort Washington State Park. So I guess we'll be hearing more about that in the next couple of months. All right, so tonight we have another of our returning champions, John Conrad. So John Conrad's career was in the aerospace industry, working with unmanned missions into space. Since his retirement, he's become a NASA JPL Solar System Ambassador, and he's given us several talks before. He's talked to us about lunar science. He's talked about Cassini at Titan and Saturn. He's talked about some of the great NASA telescopes, so the Hubble and the Webb and a few others. He's talked about Rocket Science 101. He's talked about SpaceX and the other modern spacefaring companies. So tonight he's going to be back to give an updated version of his talk on the great telescopes. And this is going to include the Nancy Grace Roman telescope. So please join me in welcoming John Conrad.
So how are we doing? Is the screen sharing?
Yes. Let me just
Okay.
do a little adjustment here. There we go.
And I'll do the same, trying to get this stuff off my screen.
Zoom's wonderful, but it puts all these little bars here and there and you can't see things. Okay, so hello to everybody. I'm not with you in person tonight. I really miss out on that because you're one of my favorite groups. And we started off the look at SpaceX and the Seven Little Dwarves, you probably remember, just about a year ago. And I've given that talk now half a dozen more times. And it was amazing how many changes I had to make to it over the year because it was such a busy year for rocket ships and for orbital launches. And I wish that were the only thing that had been busy for regarding SpaceX. But at any rate, great things have happened with regard to those particular rockets, and it was fun to talk about that last year. So tonight, we're going to talk about something that you folks are quite familiar with, and that is the ability with large telescopes, not just to make things bigger and a bit brighter, but to look very deep into space. And NASA has given us several wonderful machines to do that, or I should say, we as taxpayers have purchased through NASA several wonderful machines. And for my money, it's one of the best investments we'd made in scientific advancement and understanding the cosmos. So first off, of course, is the great Hubble. And here it is in low Earth orbit with its sunshade open on one end there. And so those two things I want you to think about. In a low Earth orbit like this, it goes around the Earth about 15 times a day, which means they have to open and close that sunshade to protect the optics. So when you hear about these deep space looks with Hubble, you can imagine just how much of a dance it has to do to accumulate not just hours, but days and weeks of staring at the same tiny bit of sky and how precise the orientation has to be. So it's quite an incredible machine. So that's in low Earth orbit. And now we have a companion that looks overlapping with Hubble's wavelengths, but further into the infrared by design. And we'll talk about the James Webb Space Telescope. And one of the very big differences, of course, is where it is. And by design, it's been put way beyond Earth in the Sun-Earth line, almost 1 million miles out to one of the Lagrange points for a couple good reasons, which we'll talk about. And then finally, we're going to finish up the 3 great optical telescopes with one that, believe it or not, you may know this, but the Nancy Grace Roman is coming up maybe to be launched next year or not later than the year after. So that will be really great because it does a nice job of complementing the other 2, as you'll see. And so let's get on with it. I made up these slides for some audiences that aren't quite as well versed in astronomy as you folks. So bear with me. Some of this may seem a little too fundamental, but it's nice to understand what it means to look deep. We aren't just magnifying things. We aren't just making nearby things brighter. We're actually looking not just deeply across space, many light years, but we're looking back in time. And you understand how a telescope actually is a time machine in a certain sense. Simple examples, if you go out and look at the moon, you're not actually seeing it. You're seeing what it was about 1.3 seconds ago because the speed of light takes a while. And so even though it's quite close, it still is a finite speed. So it takes a while. If you go to the beach and lie there and feel the warmth of the sun, somebody could turn the sun off and you wouldn't know it for about 8 minutes. And even more impressive in terms of looking deeply is looking across our galaxy at the familiar constellations and asterisms. And believe it or not, those 7 stars in the Big Dipper, the light that you're actually seeing when you look at them now, for a lot of you, started before you were born, and in the case of some of us that are a little older, started towards us when we were just babies. And that's the youngest of the stars, the 80. Some of them are in the 90-year range. So that's what we mean when we say we're looking back in time. The things that we see are actually things that happened many, many years, millions of years, and sometimes billions of years ago. Because the speed of light is finite, and go around the world over 7 times, which seems very fast, in a second, and multiply that by 60 to a minute, and 60 to an hour, and 24 to a day, and 365 to a year, and you get about 6 trillion miles for a light year. So it's amazing how far you go in 1 light year. And the universe is many of those, as we know. And it's not just huge, but you folks know this, and a lot of others don't. It's always expanding, always. And so, thanks to Hubble, and thanks to modern telescopes other than Hubble as well, and modern astronomy, we've now been able to pin down the time back to the Big Bang, when this singularity with exactly the same amount of energy and mass that we still have, because it's all conserved in an infinitesimally small spot, exploded in a Big Bang and began the universe. And so that's been expanding ever since. And so when we look back after these billions of years, we're able, hopefully, if we have really, really good telescopes, to look not just great distances, but very long look back times. So a quick pictorial, if you will, of something that you folks are very aware of, which is that every photon that's emitted is emitted in one of these frequencies across the electromagnetic spectrum. And I like the graphic because it illustrates the fact that we go from extremely high frequencies and extremely short wavelengths and high energies in the gamma ray spectrum across through X-rays and ultraviolet, and finally get to where we have evolved these wonderful sensors that can only see in this particular range. That's what the rods and cones are for. They're to see in the Roy G. Biv part of the visible spectrum, not into the infrared or the ultraviolet. And so then the waves get longer into the infrared and so on out to radio waves. And so you can think of it as stretching from left to right. So again, as I said, the universe has been expanding, and it's not that you have a whole bunch of space and all the matter expands into it. It's a matter of the fact that space itself expands, which is kind of mind-blowing. But what that means is that all these photons traveling across the universe are stretched over periods of billions of years and stretched to longer wavelengths, which means toward the right or toward the red. So we have this measure of stretching that is correlated with time that the photons have traveled, and that's redshift. So that if you have a typical galaxy which has a cutoff in the ultraviolet for the signature of the galaxy of hundreds of millions or billions of stars, and after a period of time of billions of years, you no longer can see it because all those ultraviolet and visible wavelengths have been stretched into the red, and we find the same signatures over here in the infrared. That's how redshift works, and that's why we want telescopes, if they're going to look far, to be able to look in the infrared especially, because those are the things that are the oldest. Another thing to think about with regard to these telescopes is why we have them in space. And again, you folks are familiar with a lot of this, but the very short wavelengths are all blocked to a large degree by the atmosphere. And there's a hole where we have evolved to view things in the visible range there. And so we see quite nicely through the atmosphere, and we can see a little bit, or I should say, ground-based telescopes can see a little bit into the infrared, but most of the infrared is blocked. And then you get another hole in the atmosphere for transmission out for the radio telescopes. But because of this, if we want to see in all the wavelengths, we have to go above the atmosphere with space telescopes. And so here's an artist concept just illustrating that. But here's the real one that we're going to talk about, the Hubble. And it's positioned where it looks, which is from a little bit of the ultraviolet across through the visible into the near infrared. And for about 2 decades, we had the Spitzer infrared telescope, and it was able to see, but not with very sharp resolution, way into the infrared. And it's now been retired because essentially it got too warm, which for viewing the infrared means that you don't have great sensitivity anymore. So it's been retired. And so now we have the James Webb, which nicely covers the area from a little bit of the visible across through the near infrared and well into the mid infrared by design. And we'll talk more about what it's able to show us. So a quick and easy graphic to just kind of illustrate the history of the universe in one slide and what it means to us for these telescopes. And that is that the Big Bang was way over here in the lower right, and some 13.8 billion years later. And I have to ask, are these slides showing up, or do you have bars that are blocking parts of them? Can you see the yellow arrow at the bottom?
Yes.
Good, okay. Because I can't get this bar out of the way on mine, so I can't even see it. At any rate, so here we are today, over at the left there, with the Hubble looking back towards as far as it can in terms of look back time. And it can't see all the way back to what we believe from our cosmology to be some of the most interesting events, like when the hydrogen and helium formed the first of the stars, which we think was about 200 or 300 million years. But we can see quite a way as it turns out. And so after the Hubble was launched in the 90s, after a few years, they picked an extremely dark spot, tiny spot, like a grain of sand held at arm's length, if you can picture an area that tiny, and they stared at it for a long time and created the first very exciting Hubble deep field, the HDF there, which, as you can see, got us back, and this surprised a lot of people, all the way back to the first billion years after the Big Bang. And then after 5 visits by shuttle astronauts, which is something we can't do with the current telescopes, we were able to not just correct the optics initially, but change out each and every instrument to where it's a brand new telescope. And by 2009, they had all the new instruments and were able to stare even more deeply with the better sensitivity and filters and infrared sensors, and create this Hubble Ultra Deep Field, which surprised a lot of people by how far back it could see. And we'll show you what the record is in just a minute. But here is a look at a particular part of the sky that's been studied by staring with many telescopes, not just the optical telescopes, but also X-ray and others at this area. But what we're going to focus on is where Hubble created the deep fields. And so the ultra deep field, as I said, was the one that they were able to do with the new instruments about 15 years ago. That's in red there. And that was an accumulation of 11 days of staring at this seemingly blank little dot in space. And then after a few years, they actually used a greater length of staring and came up with the extreme deep field, which you see here, and doubled the time. And so let's take a look at that extreme deep field. There it is. 10 billion times as dim as the naked eye can see. 5,500 galaxies in this image. none of those things which look like a starry sky are stars. They're all galaxies and extremely far away in many cases. And so I wanted to pause, and I've shown you this before, but I've kind of worked on this slide because it's a tricky one to understand. And I like it because it reminds me of how redshift works. But I want you to note, first of all, this gray area of energy that's being viewed and how there's a sharp drop off at the left end, which if you can read the wavelength there, is down below the blue of the visible spectrum into the ultraviolet. And that's what's known as the Lyman break. And you can read about that more easily than I can explain it. But basically, it means that to the left of that, there isn't enough energy that these telescopes can actually see anything below that limit. And so when you see the energy of a Lyman break galaxy, you see this nice drop off as a signature of it. And that's a nearby galaxy where the energy hasn't been redshifted because it's near to us in time. And so now let's take a look at what happens when we allow the universe to expand, shifting all the wavelengths so that we now are looking at a galaxy, as you will see, that gets redder and redder. And I messed that one up, so we'll be back here in just a second. And so here you can see the Z number is the redshift, and it gets higher and higher as the energy and the wavelengths are shifted more and more into the red. And in the case of Hubble, it can only see out as far as these 9 filters that you see labeled across the top, from 0.435 microns over to 1.6 microns into the near infrared. And you may have noticed along the bottom that each of those images that are shown through the filters disappear as there's no energy coming through that filter. And so you can make a quick photometric estimate of the redshift by picking off which filter allows the blob to show up from this very distant object. So that's the way the redshift is used to show you how much look back time you have from your telescope to that object, which is correlated to time back through the billions of years of the universe. And so the record, after about 22 years, I believe, or 24 years of Hubble observations, looking in the deep field with lots of researchers trying to set the record for what they could find, is one that's labeled here as GNZ11. Goods north is the area of the sky, and Z is the redshift. And it correlates, and this surprised a lot of people, to about 400 million years after the Big Bang, or roughly 97% of the time back to the beginning of the universe. And I have to say that probably the developers and astronomers in the 90s, first of all, it took Hubble and other telescopes late in the 90s to understand and better estimate the age of the universe. But I don't think anybody expected that we were going to be able to use this machine to see back that far in look back time. But it happened, and it's extraordinary, and it's still operating great at this point. And so now let's take a look at what's coming later, or coming now, looking even deeper with a better telescope to look deep. And that is the James Webb over there now at the left. And the belief is that with the infrared sensors and the cooling that we'll talk about, that we're going to be able to see much, much further in terms of redshift, perhaps out to the first 200 to 300 million years after the Big Bang, which is the time of certainly the first galaxies and the first stars possibly. So a quick reminder of these two machines to contrast them. They aren't shown to scale here. The one on the left there, the Hubble, is about the size of a big school bus with this nice about 100-inch mirror, 2.4 meter diameter. And the James Webb has this huge primary, more like, what is that, roughly 260 or so inch diameter mirror, the segmented mirror, with a light collecting capability 6 times greater. So we're going to get much better resolution and much better ability to collect dim lights across the universe with this. And to illustrate just how large the James Webb is, this 5 sunshade that you see in the bottom, the blue layers there that are spread apart, are each larger than a tennis court. And so you can see just how large this machine is. And they sort of dwarf the telescope above it and all of the instruments that are kept on the cold side of these sunshades. The key to being able to see in the infrared, among other things, is to be able to look and with a cold focal plane or a cold camera film. And so the Hubble was actually a room temperature spacecraft. And so it's cold in there, but it's not nearly cold enough to see very far into the infrared. And you contrast that with the James Webb, which by design has all of the instruments at least as cold as about 388 degrees Fahrenheit below zero. Not that far above absolute zero. Very good for seeing in the infrared. You guys like information about the optics, so I thought I'd put this up. Maybe it's just a reminder, but with the Hubble, which is a Ritchey-Chrétien Cassegrain, we have the perfect hyperbola, which wasn't perfect and had to be corrected with the first visit by shuttle astronauts in 1993, with the secondary, a parabola and a curved focal plane. Contrast that to the James Webb, which is a 3-mirror and astigmat, which may mean something to you folks. So we've got this parabola with a secondary that's hyperbola, and to remove the astigmatism in the tertiary and flatten the focal plane, we've got that so that we have a much larger focal plane compared to Hubble at a much, much colder temperature. So there it is with its 18 segments. And for scale, you see the guy in the clean suit standing on the floor in this huge clean room. And you see the tripod holding up the secondary there, reflecting the light back down the center of the primary to the tertiary and the instruments. And of course, at this size, which I think I said was at any rate 6.5 meters, so whatever that works out to, well over 20 feet in diameter, this huge spacecraft was going to require something to be done to it in order for it to fit on top of any rocket. And so here's what they were able to do with it: fold back 6 of the segments on the sides and take that 5-layer sunshade and close it, and then roll it together, and then fold those up and stow them on the sides in order to get it to be a small enough diameter to fit inside a fairing of, in fact, a very huge rocket, as you'll see, but small enough to fit. And again, you folks like telescopes, so just a quick reminder, each of those segments is identical at 80 pounds and about 50 inches in diameter, made of beryllium because they won't have any expansion contraction in the range of operation, with a highly reflective layer of gold. And critically, the shape. And the shape has to be formed by something that's been folded up and then has to be unfolded in space on its way to its rendezvous point, or I should say its end point. And not only does the shape have to be, and each of the segments have to be oriented correctly, but the figure for the reflector has to be perfect. And so they have these actuators 7 on each segment that tip and tilt each of the segments initially to give you the gross shape of the telescope primary. And then one of them is on the back of each of the segments that can push and pull. And they did this for a period of about 2 weeks or so when it had gotten down to the proper temperature in order to form the perfect telescope figure. And so it's working just extraordinarily well with all of these mechanics required to finish the shape in space. So there it is on Christmas morning, a little over, 3 years ago, on a very heavy launch vehicle that we contracted the European Space Agency to launch for us, partly because it's such a heavy lift vehicle, but partly because in order to get that large a payload properly on its trajectory, we wanted to use the Earth's rotation, so you want to be close to the equator. And the French Guiana launch site for the European Space Agency on the East Coast gives us a lot of that rotational energy of the Earth to use. And it was such a perfect launch provided by the Europeans that they used very little in the way of propellants after the second stage was fired, and then deployed the James Webb spacecraft so that they didn't need to do much course correction going out that almost 1,000,000 miles, and saved a lot of the propellant that now can be used to extend the life of the telescope during its station keeping while it's on orbit. And so here's where it is. It's in the Sun-Earth line, about almost 1,000,000 miles out at what's called the Lagrange 2 point, which is a stable point in this two-body system. And as I said, it took about a month to get out there, and it went through this self-assembly of many, many steps. And I cannot imagine the anxiety that some of these people that had worked on the design and the instrumentation and planned the research projects and prepared the teams for not just a decade, but in some cases 2 decades, while they waited to see after the launch if it would get there and if it would all work properly. And once it got there, it was working great. They shaped the mirror, cooled it down, and finished the configuration and declared it operational. And so here is where it is in operation. While they took it out to this stable point, what they didn't want to do was try to station keep it actually in the Sun-Earth line for a couple reasons. One is they didn't want to drift in and out with the associated thermal expansion and contraction of the eclipse. And they wanted to be outside of the Sun-Earth line so that the solar panels could always see the sun. And so there you see it in its configuration where it always keeps that 5-layer sun shield between the business side and the sun. Here are the 4 instruments that were developed and launched with it, each quite an extraordinary development. The US on the top left, the Canadians in the lower left, and the Europeans in the lower right developed these 3 near-infrared instruments. And the Europeans also developed this extraordinary mid-infrared camera and spectrometer, which doesn't just operate at 40 degrees Kelvin, but it operates at 6 degrees Kelvin with active cryogenic cooling. So quite an extraordinary set of instruments that can see way out into the infrared now. The one in the lower right there, I like to highlight simply because it's got an engineering feature that I love. Here we're looking at a globular cluster, which of course you folks are familiar with, and they are extraordinarily dense in terms of the number of stars in the small volumes towards the center. And so, for example, here's a very small area of the center of this globular cluster. And here's a focal plane image of what is seen with the light coming through James Webb's mirror systems. And it can obtain up to 100 stars simultaneously. And the way it does this in this very densely populated environment is using this feature called a micro shutter array, where you have 62,000 individually addressable shutters that can be magnetically commanded to open and close. Each of them is the size of less than a human hair to allow that light through. And so you can decide, and you can get all of these simultaneous stars and look at the spectra of all of them from the same viewing. Quite an instrument. The science goals overall are ones that you would kind of expect from what I've said, looking back with long look back times as early as we can to see the first galaxies and luminous objects, hopefully even back to stars. Because we can see at all slices of time from today back to only a few hundred years after the Big Bang, we'll be able to see enough galaxies to hopefully be able to understand better how each galaxy evolves and merges and how they are actually assembled toward the beginning. And then in number 3 there, not just those images of the protoplanetary disks that you see 4 of there from Hubble, but we're going to be able to actually see these disks before the stars have started to fuse in the center, and be able to see them with better resolution, and hopefully be able to learn some things about the development of planets in those protoplanetary disks. And finally, for the more nearby planetary systems, we'll be able to see things about the atmospheres of the exoplanets and the composition, and understand more about the origin of life and connect it to different possible star systems and exoplanets. So here is the comparable deep field created by the James Webb very early on. And one of the most interesting features of this one, you remember the extreme deep field of Hubble had about 5,500 galaxies. In this one, they've been able to count, I'm not sure how they do this, about 100,000 galaxies in this tiny area. And a feature that you folks are well familiar with, I think, from gravitational lensing, these various arcs that we'll talk a little bit more about in a minute. So that's the early James Webb deep field, and there have been teams of researchers around the world competing with each other, but really competing and studying this to try to find the earliest possible galaxies. And I thought you'd be interested to know that 2 of the 4 that were found to be the earliest in the research up to the beginning of last year were by a team at Penn State and a postdoc named Dr. Binji Wang there actually found these 2 and got the credit for them. And they are respectively 330 and 340 million years after the Big Bang. The record holder through 2023 is this particular one in the JADES field, which again is in the same area that those Hubble deep fields were, with the James Webb staring there and getting something, in this case, with a redshift factor of about 13 and an age of about 320 million years. And that was at the beginning of last year. And then during last year, there was a new record holder, or new record setter, I should say, with a redshift of 14.32 now. And so that galaxy is within the first 300 million years. And I thought in this case, you'd be interested in seeing the galaxy spectrum, which is comparable to that one that I had the animation for before, where you can see the Lyman break there, which is in this case is sitting out at about 1.85 microns in the infrared and started over somewhere around 0.1 before it was redshifted. Some of the other findings in the first year and a half or so of research, they have found many early galaxies that are very large and bright, which is not what they expected. This is one of the mysteries that presented itself almost immediately across many teams. And so this is one that they're working on right now. They were able to find an individual star. It's not one of the earliest stars. And in fact, it had been seen earlier by Hubble and identified. It's called Earendel. And you can see it from the inset box there blown up on the right as part of this, gravitational lensing arc. And its look back time is almost 13 billion years. So we're seeing a star that was only about 800 million years after the Big Bang sitting by itself that they're able to see. I wanted to note also that they've been looking somewhat just across our neighborhood here. And so here's a picture of Uranus illustrating 11 of the 13 rings. And you're probably familiar with the fact that this particular among the 8 planets is unique in being tipped almost 90 degrees in terms of its polar axis pointing back toward the sun. And so that's what it looks like with the James Webb. And I thought it was kind of interesting to contrast the resolution that we're getting there with the James Webb. And you should understand that in a general sense, the resolution is worse in the infrared because of the wavelength being longer than it is able to be. You can see things more sharply in the visible bands. And to illustrate that, we'll look here at what the Hubble saw of Uranus, looking at it over 3 different years, 2003, 5, and 7. And the fact is that the period of Uranus is 84 years. So over a 4-year period here, you're seeing a fair amount of turn of the polar axis, if you will, or I should say of the face as it comes into view, looking at it from Earth or near to Earth. And you can see the rings closing there. And then it was interesting also, I thought, to look at the resolution that we're able to get now from ground-based telescopes. And the Keck, like other 400-inch diameter, roughly, ground-based telescopes with this incredible invention of adaptive optics, was able to get this kind of sharpness in looking at Uranus and its rings at about the same time that Hubble did. So in fact, with the larger mirror and the adaptive optics, even though we're looking from the ground on the Earth as opposed to out in space, we get a sharper look with Keck. So now we'll look at planets outside the solar system, and of course not outside the galaxy, because we wouldn't be able to see anything like this outside the Milky Way. But they've been able to find a particular planet and image it with the coronagraph on the James Webb. It's about 385 light years away. It says it's in a special constellation called Centaurus, which is a lot like Centauros, which proves that astronomers don't spell that well. But at any rate, you see in 4 different frequencies, 4 different wavelengths here, a view of the planet, where the star is, in fact, on each of these images, the star, and it's blocked out as a coronagraph does, so that you can see what's close into it, and the planet is visible there. And in the case of the shorter wavelengths over here on the left, you've got these artifacts that you see, and that's not actually the planet, that's just an artifact of the viewing process in those particular filters. And I'm going to finish off the web stuff, even though there's been an extraordinary amount of results from the research so far, with a look at what these astronomers technically refer to as little red dots, which if you go back to that James Webb Deep Field and you look at it, you can start to pick them out. And it turns out that every image that they've found so far from James, or looked at so far, is populated with many, many of these little red dots. And with the Z numbers, the look back time means that they're all about 500 million to 2 billion years in terms of age after the Big Bang. And then there aren't any more after 2 billion years. And so lots of researchers have been trying to figure out what these are. They're too big and they're too luminous to have been around that early based on the various theories that we've had. And so here's a look at a Penn State researcher that spoke to our astronomy club in Chester County over at Westchester University about a month and a half ago. Joel Leha gave us a fantastic presentation. And I recommend that if you guys haven't heard from him yet, heard his talk yet, but he's been leading one of these teams, and their team has been focused on the little red dots. And at the conclusion of everything he told us that they had tried to figure out about them, he said that one of these three things is true. Either our understanding of galaxies and their formations is very wrong, or our cosmology for the first few 100 million years of the universe is flawed, or they're not galaxies. They're huge, supermassive black holes, which doesn't make any sense at all how in the world those could be formed. And so this is a big mystery, and there are quite a few teams that are studying this one right now. All right, so to move on from what we now have to what's coming soon, that's going to be complementary to the Hubble and the James Webb, we're looking at this artist concept of a wide field space telescope known as, excuse me, the Nancy Grace Roman Space Telescope. And you may know about her. I think it may be Women's Month, Women's History Month, so this is timely. But at any rate, Nancy Grace Roman, shown in this picture kind of in the latter part of her life, I think maybe in the last 10 years. I think she passed away since then. But as a young woman, she was quite a well-known astronomer in the middle of the last century, to where when NASA had just been formed in '58, in the 60s, there were enough researchers and scientists that knew about Nancy Grace Roman that they got her appointed to be NASA's first chief astronomer. And she did quite an extraordinary job, not just of getting NASA's astronomy program started in those early years with things like the OAO, the Orbiting Astronomical Observatory, but she also was an effective lobbyist, if you will. And so she saw the need and the value of a space telescope initially and took it out and convinced a lot of people and got the nickname the Mother of Hubble. So she's now been blessed with being named, having a telescope named after her. And the Roman was a particular kind of telescope that was established as the top priority by a bunch of astronomers that get together every 10 years under the auspices of the National Research Council and give out their recommendations in a decadal survey. And so the top billing was given, let's get a wide field infrared space telescope, because it's great that we've got Hubble and now Webb, but they see these tiny little areas, and we'd like to be able to do surveys more. And before very long, an organization that you may or may not know about, the NRO, the National Reconnaissance Office, was known only to lots of us that had very deep clearances in the intelligence world before the mid-90s, but then they came completely out into the open. And so now you can understand that that's the organization that has managed a lot of the spy satellite and that kind of surveillance work that's been going on for decades. And they had two unused space telescopes that they'd contracted for and had built, and they didn't need them. And they offered them to NASA, and NASA accepted. Turns out that, like Hubble, they're 2.4 meter, like the and you can now understand the correlation between what we've been using for our Hubble Space Telescope and some of the reconnaissance missions where they don't look up, they look down. And so the folks that were doing WFIRST accepted the offer, and it saved them hundreds of millions of dollars. And subsequently, they've been able to move forward much more rapidly, and the launch is now planned for next year or the year after. It'll be going out to the same nice cold place that the James Webb is. And here's the main feature of it that allows it to be so special with its very large field of view, with 18 squares of essentially 16 million pixels. Mercury cadmium telluride, infrared sensors, about, what's that work out to? About 300 million pixels, and it's going to operate not quite as cold as the James Webb, but very cold in order to be sensitive in the infrared. And it's going to be looking in a range that kind of overlaps a little bit with Hubble and a little bit with Webb. So it's going to see higher redshifts than Hubble and lower than Webb, certainly. But the key, of course, is this wide field and being able to do surveys. The particular thing that one of the two instruments, the wide field imager, is going to be focused on is to look out in the Milky Way bulge and try to learn a whole lot more about the exoplanets that are in a particular domain of distance and brightness and or mass compared to the ones that are being found by Kepler so far. And so by doing what's called microlensing surveys, and you understand what gravitational lensing is and the arcs that you see in the images, and that's kind of the generic term for any time where you're seeing a distant object magnified and distorted with its light coming around a large mass in between. And typically the large masses in these deep fields is probably galaxy clusters, something like that, which are huge masses that can gravitationally bend that light. Gravitational microlensing has the lensing star be just a single star, not be a galaxy or a cluster of galaxies. And so they're going to be looking for what they can find in the way of planets in larger orbits around stars in the fairly nearby neighborhood of the Milky Way in the bulge. And we'll see how they can do, but they're believing that they're going to be able to fill in a lot of the blue part of this domain, where the x-axis there goes as distance away from the star to the right, and the y-axis goes as increasing mass of the planet. So far, the red ones have been what Kepler's been able to find, generally smaller and closer to the star, and we expect WFIRST to fill in a lot out there. The other instrument, which is very interesting, first of all, because of its size to me, it's about the size of a baby grand piano. It's got all kinds of lenses and mirrors and such things in its optics. And so instead of having a paddle that blocks out the light of the star that you're trying to see things close to, like a typical coronagraph that you've probably seen with the solar spacecraft that are looking at the sun with a paddle that blocks out the sun so we can watch comets move in and around the sun as they go around. But in this case, it's not a physical paddle, it's a set of deformable mirrors and lenses and stops and so on that is theoretically at least going to allow them to see much, much closer to individual stars, really block out the light by a factor of about, I think, 10 to the fifth greater than what we're being able to see with current coronagraphs. So in one sense, this coronagraph is just a technology demonstration. But if it works, it's going to be extraordinary that we can see things very directly and image directly planets out to 30 or 40 light years by using this particular technique. So that's what's coming. I just wanted to quickly wrap up with a summary that these three telescopes, which are complementary, were successfully, or I should say successively, conceived and then developed and built and launched more rapidly, which isn't the way things typically have been happening lately. But after about 30 years, we finally had a working Hubble, and it's still operating with all new instruments these decades later. The James Webb took a bit less time, but still it was quite a while for a lot of the people that were starting to do their research proposals about 20 years before it was launched. And now, hopefully, since it's operating so well, it'll last a few decades. And the Nancy Grace Roman has really come along in a very rapid fashion here, thanks to the donation of those two existing 100-inch telescopes. So the three complementary large space telescopes, I thought you'd be interested of what they cost since we bought them. We're the taxpayers. $25 billion, for my money at least, is an incredibly good investment for what we've gained here in terms of astronomy and physics on the large and small scale advances. It's just remarkable how fast we've moved forward. And I thought it was interesting to contrast that price tag to the fact that the moon rocket that still hasn't carried any crew on board yet, and may not for another year or more, has already cost over 4 times that much, and will cost a lot more than that by the time we actually put people on the moon. And so one of the things that this illustrates to me, and I'm just deducing this, I don't know it, but it seems like the appetite to spend huge amounts of money for something that actually involves people being involved in moving forward a frontier is viewed as much higher value than just sending robots or using robots to do the job. I've got my own personal opinion of that, and I may not agree with it, but it does seem to be what we're able to do to attract the most money. It's what happened in the 60s with Apollo. We spent an enormously large portion of the nation's economy in the 60s and have never spent anything like that percentage since. And so we'll just have to see what happens with manned exploration now going forward. Anyway, that's it, folks. Thank you, and I'm open to questions if you have any.
Thanks so much, John. That was great. I just love that story about the NRO just basically saying, oh yeah, we've got an extra Hubble mirror laying around that we're not using, so
Yeah.
we've got better stuff. Great. Questions?
turn this speaker down a little bit,
A little too hot for you?
way up. Have a seat in this chair and see what you think.
You're in the firing line.
Yeah,
Do you have a question?
no.
All right, questions? You're in the spotter zone.
I'm picturing a room full of people that's been rendered deaf now.
He's just sitting right in front of the speaker.
Okay.
Jeremy's keeping its distance.
Yeah.
Well, okay, well, thanks very much, folks. I always appreciate the opportunity to talk to you. So if there are any questions. Thank
Yeah,
you.
we have a few questions. We just have to move some people because they're in front of the speaker. We're getting a lot of feedback.
Thank you very much for the talk. I don't really have as much of a question. I'm just curious more about like the James Webb and like exoplanet like detection. If you could talk more about that, if you know more.
I don't. I'm an honest man. I won't try to wing that one.
Yeah, thank you again for your talk, and all of this is sort of new to me. I was curious, are there other space telescopes out there or only the ones that NASA has sent? You know?
Yes, there are certainly others. Boy, I wish I had a slide or two on them. The Europeans have had one called, I believe it's Gaia. Have you folks seen that one? That has been out there doing a survey, literally a survey of the Milky Way, extraordinarily detailed. And as a matter of fact, the data from I think it's just been retired. I may be wrong, but I think I read that recently. But the database, the image with its incredibly large number of pixels is available. It's publicly available online. If you just look it up, you can look at different segments of the Milky Way if you want to. And the Europeans have had, trying to remember, I think they had one infrared telescope. I'm not sure. But yes, there have been others, at least the European Space Agency. And I don't believe the Japanese or the Indians or the Russians or the Chinese have yet launched any. But if you were asking, do we have others? Yes, we've had a number of others in the gamma ray, the ultraviolet explorer. They're trying to think is I don't think there's been an X-ray, a gamma ray, and an ultraviolet. I don't think there have been any space telescopes at the longer wavelengths beyond IR.
John, could you say anything about the SphereX scope that was just launched a couple of days ago?
Again, I must apologize. I have read probably about the same that you have, a couple articles, but a lot of it slipped my mind. So I'd just be trying to remember a couple facts, and I don't actually remember much about it.
Yeah, I'm kind of curious about how that complements this.
Yeah, good question. I don't know the answer.
Other questions? Going once, going twice. All right, got another taker.
Try again.
Thanks again, John. Are there any like resources you recommend for like, you know, all the science is coming out, but I'm not a scientist. Like, what would you recommend to like, you know, stay on top of what's coming out of like the web or whatever?
No, I don't. Let's see. I do a very unsurprising kind of research when I prepare my talks. I get some of the material from NASA, but in this case, and you know, maybe half the slides were drawn from NASA. the slides that we got from Dr. Joel Leha at Penn State, who again, I really recommend if you guys haven't gotten a talk from him that you see about that. He's an excellent presenter too. But he's one of the researchers working at the forefront, and he could answer that question in just a second. But my point is that NASA makes it very easy to search all of their missions and to do a deep dive on what's available in all of them. And they've got a lot of databases from things like their infrared, the Spitzer Space Telescope and Hubble, and all of them. You can find the imagery databases, and sometimes you can actually find the actual data sets that are used to produce these things without much trouble. Just do it by doing data searches. And Wikipedia has got an extraordinary amount of detail about all the different space telescopes too. But as far as specific web stuff, I think probably just reading the, the journals that we all know about, Sky and Telescope and Astronomy, and being on the websites that like Earth Sky and things like that, allows us to see the things that make headlines pretty quickly. But as far as actually getting insights into the research, I don't have any way to do that. I probably could check with the people at NASA, but have never taken the time to do that. We just sort of wait and see what topics they're going to present to us.
Well, thanks very much, John. That was fantastic. And thanks, Jeremy, for the good technical execution of this remote meeting. It worked really well.
Thanks a lot, folks. Take care. Bye-bye.
To address the question about what's a good way to follow up on these things, I'd like to echo what John said about the two publications that are most read by a lot of people in this room, Sky and Telescope and Astronomy Magazine. And if you're brand new, start out with Astronomy Magazine. It's a little less technical. And at our website there, at the very bottom, scroll down to the bottom of the homepage, there are links where you can get discounts for those magazines, and you can get a digital version or print version. And I'd encourage everyone new to do that because it's worthwhile for sure. Okay, well, thank you everybody for your good questions and for your attendance tonight. I'll say goodbye to everyone on YouTube.